Cylindrical and spherical coordinates. In the rectangular coordinate system, when we're plotting a point, the coordinates of the point have the form x, y, z. We can think of that point as being the corner of a rectangular box, which is where the term rectangular comes from. To plot the point, from the origin, we move x units along the x-axis, then y units parallel to the y-axis, and then z units from the xy plane. A point in rectangular is the intersection of three planes. If we take the set of all points with the given x-coordinate, we have a plane parallel to the yz plane. If we take all points with the given y-coordinate, we have a plane parallel to the xz plane. And if we take all points with the given z-coordinate, we have a plane parallel to the xy plane. The intersection of those three planes is that point. In cylindrical, our points will have the form r theta z. The r and theta are the same r and theta from polar coordinates. So if you're already familiar with polar, you're in good shape here. And the z coordinate, z, is the same as the z in rectangular. We're moving perpendicular to the xy plane to get to z. We could think of that point as lying on a cylinder, where from the origin, we come straight out r units in the xy plane, making an angle of theta with the positive x-axis, and then we go straight up z units. Note that there are infinitely many different ways to write a point in cylindrical. For example, if r theta z is the point, then r theta plus 2 pi z is also the same point. We can replace theta by theta plus any multiple of 2 pi and we get the same point. Another way to get the same point would be to use a negative r value and to adjust theta by pi. To guarantee that there's only one way to write the point, we'll insist when we write down a point that r is non-negative and theta is between 0 and 2 pi. 0 can be used, 2 pi should not be used, because if theta is 0 or theta is 2 pi, you would get the same point. Notice that when you think of a point in cylindrical, you're thinking of it as the intersection of two planes and a cylinder. The cylinder has equation r equals some value. Just like in rectangular, the z-coordinate leads to a plane, and the theta coordinate also leads to a plane, the plane that starts with the z-axis and comes straight out along the ray that is determined by theta. In spherical, our points have the form rho theta phi. We could think of our point as lying on a sphere. To get to the point, we come straight out from the origin rho units. Theta is the same theta that we use in cylindrical. It's the angle in the xy plane that we make with the positive x-axis. And phi is the angle that we make with the positive z-axis. Just like in cylindrical, since there are infinitely many ways to write down a given point, we could make that unique by insisting that rho is non-negative, theta is between 0 and 2 pi, including 0, but not 2 pi, and phi should be between 0 and pi. In the case of phi, we include both 0 and pi. A point that has a phi coordinate of 0 is on the positive z-axis. A point that has a phi coordinate of pi is on the negative z-axis. Just to give one more example, if the phi coordinate is pi over 2, then the point will be in the xy plane. It's halfway between the positive z-axis and the negative z-axis. Note that when we plot a point in spherical, we're thinking of it as the intersection of a sphere, a plane, and a cone. The sphere is given by the rho coordinate. The plane is given by the theta coordinate, just like in cylindrical, and the cone is given by the phi coordinate. To help clarify what I just said, let's look at a specific point, like 1 pi over 4 pi over 6. We're thinking of this as in spherical. So rho is 1, theta is pi over 4, and phi is pi over 6. Since rho is 1, we know that the point lies on a sphere of radius 1 centered at the origin. Since phi is pi over 6, we know that the point lies on a cone that makes an angle of pi over 6 from the positive z-axis. Notice that the intersection of the sphere and the cone is this circle. So our point lies on this circle that is the intersection of the given sphere and cone. The plane defined by theta equals pi over 4 intersects that circle in a unique point. Now let's learn how to convert points between the various coordinate systems, starting with converting between rectangular and cylindrical. Here we have a point written in rectangular as x, y, z, which means we go x units along the x-axis, y units parallel to the y-axis, and z units perpendicular to the xy plane. Now, if we want to think of that same point in cylindrical, then we're going to go straight out in the xy plane from the origin, r units, making an angle of theta with the positive x-axis. And then we go straight up z, just like we did in rectangular. Let's just look at that triangle that was formed in the xy plane. Notice that in the xy plane, we go x units along the x-axis and then y units parallel to the y-axis to get to the point, if we're thinking of it in rectangular, or we go straight out from the origin, r units, making an angle of theta with the positive x-axis if we're thinking of it in cylindrical. Or we could think of that as polar in this case, since we changed the picture to a two-dimensional picture. Notice that x is equal to r cosine theta and y equals r sine theta, just from basic trigonometry. These are the same transformations we have for polar coordinates. And similarly, x squared plus y squared is r squared, and the tangent of theta is y over x. Again, that's from basic trigonometry of the right triangle, or just remembering that those are the polar transformations. Finally, z is just equal to z. In other words, we're using the same z value for both rectangular and cylindrical. Let's try a couple of examples. Go ahead and pause the video, try these examples yourself, and then resume the video to check your answers with mine. First, convert 8 pi over 3, 7 from cylindrical to rectangular. Okay, so we're thinking of 8 as the r coordinate, pi over 3 as the theta coordinate, and 7 as the z coordinate. So the x coordinate is 8 cosine pi over 3, the y coordinate is 8 sine pi over 3, and the z coordinate is 7. So the cosine of pi over 3, that's 1/2. 8 times 1/2 is 4. The sine of pi over 3 is root 3 over 2. 8 times root 3 over 2 is 4 root 3, and we'll leave the 7 as is. So we get 4 root 3, 7. So x is 4, y is 4 root 3, and z is 7. Let's look at the second example. Convert negative root 2, 1 from rectangular to cylindrical. So in this case, x is negative root 2, y is root 2, and z is 1. Let's just look at the projection of this point in the xy plane. So we're just looking at negative root 2. To plot the point negative root 2 in the xy plane, we go left root 2 because the x coordinate is negative, and then up root 2. From there, it's pretty easy to convert. R is the square root of root 2 squared plus root 2 squared, or the square root of 2 plus 2, or 4. So the square root of 4 is 2. Theta is the angle formed with the positive x-axis. So the reference angle that's inside that triangle would be pi over 4, and therefore theta is pi minus pi over 4, which is 3 pi over 4. And the z-coordinate is the same as the z-coordinate in rectangular, so we just put a 1 there. So the point is 2, 3 pi over 4, 1. Now let's go over how to convert between cylindrical and spherical. So here we have a point. In cylindrical, its coordinates are r, theta, z, which means we come out our units in the xy plane, making an angle of theta with the positive x-axis, and then go straight up z units. Now let's see what we do in spherical. In spherical, we're going to come straight out from the origin to the point, rho units, and we're going to come down from the positive z-axis with an angle of phi. Theta is the same. Now, using the fact that when you have two parallel lines cut by a transversal, the alternate interior angles are congruent, we see that we could write phi inside the triangle, the angle between the sides of lengths rho and z. Let's just look at that triangle for a minute. Notice it's a right triangle. We drew it a little funny here because it's being drawn in 3 dimensions. But if you look at this triangle, its behavior is exactly the same as the triangle we drew for converting between rectangular and cylindrical, or rectangular and polar. We have r equals rho sine phi and z equals rho cosine phi, again using basic trigonometry of the right triangle. Rho squared is r squared plus z squared. Once again, pay attention to where that right angle is. It looks a little funny because it's drawn in 3 dimensions, but that angle is a right angle. And we have tan phi is r over z, because tangent is opposite over adjacent. And finally, theta equals theta. We're using the same theta for both cylindrical and spherical. In practice, you can memorize these formulas, or you could just remember how to draw this picture. I prefer to just draw that triangle each time I need to make these conversions rather than have to memorize the formulas. That said, notice that the formulas are identical to the formulas for converting between rectangular and cylindrical, except all the names of the variables have been changed. Okay, go ahead and try this example. Pause the video, try it yourself first, and then resume the video to check your answer with mine. Okay, let's convert 6 pi over 4 pi over 3 from spherical to cylindrical. Notice that 6 is the rho coordinate, pi over 4 is the theta coordinate, and pi over 3 is the phi coordinate. Let me draw the picture. So rho is 6 in that picture, and phi is pi over 3 in that picture. Notice I don't have to draw theta in the picture because theta is going to be exactly the same. We can just copy it over. Using the picture and some basic trigonometry, or just plugging directly into the formulas, we get that r is rho sine phi, which is 6 sine pi over 3, which is 6 times root 3 over 2, or 3 root 3. The theta coordinate we just copy over, that's pi over 4. And for z, we get rho cosine phi, which is 6 cosine pi over 3, which is 6 times 1/2, or 3. So the point in cylindrical is 3 root 3, pi over 4, 3. And now, finally, let's go over converting between rectangular and spherical. There are 2 ways we can convert between rectangular and spherical. First way is just to use cylindrical. For example, if we want to convert from rectangular to spherical, we can convert from rectangular to cylindrical first, and then from cylindrical to spherical. And similarly, if we want to convert from spherical to rectangular, we could convert from spherical to cylindrical, and then cylindrical to rectangular. That said, I'm going to show you what direct formulas you get if we copy that procedure in general. So here's a picture of the triangle that we have for converting between cylindrical and spherical. And writing down the formulas for converting between rectangular and cylindrical, we have x equals r cosine theta. And if you look at the picture, you can see that r is equal to rho sine phi. So we have x is rho sine phi cosine theta. Similarly, y equals r sine theta. And again, r is rho sine phi. So y is rho sine phi sine theta. To get z, you could either use the picture, or if you have the formulas memorized from converting between cylindrical and spherical, we know that it's just z is rho cosine phi. For the other direction, from the picture or the conversions between cylindrical and spherical, we have rho squared is r squared plus z squared, but r squared is x squared plus y squared. So rho squared is x squared plus y squared plus z squared. Tangent of theta is y over x, and cosine phi is z over rho. But rho is the square root of x squared plus y squared plus z squared. So cosine phi is z over the square root of x squared plus y squared plus z squared. Okay, let's try some examples of converting between spherical and rectangular. Pause the video, try these yourself, and then resume the video to check your answers with mine. First one, convert 6 pi over 3 pi over 4 from spherical to rectangular. Okay, just plugging into the formulas. X is rho sine phi cosine theta. So that's 6 sine pi over 4 cosine pi over 3. Y is rho sine phi sine theta. So that's 6 sine pi over 4 sine pi over 3. And z is rho cosine phi. So that's 6 cosine pi over 4. And our final answer is 3 root 2 over 2, 3 root 6 over 2, 3 root 2. Now convert 4, negative 4, 4 root 6 from rectangular to spherical. Let's draw a picture of the projection of the point into the xy plane. So we're just looking at the point 4, -4 in the xy plane. We go right 4, down 4. We go down instead of up because the y coordinate there is negative. So from this picture, we see that the angle theta is 7 pi over 4. We get that by taking 2 pi minus the reference angle of pi over 4. Right? 2 pi minus pi over 4 is 7 pi over 4. And we could get rho by taking the square root of x squared plus y squared plus z squared. So that's the square root of 4 squared plus the square of -4 plus 4 root 6 squared, which comes out to 8 root 2. And finally, we could get the phi coordinate by seeing that cosine of phi is z over rho. Z is 4 root 6. Rho we just found to be 8 root 2. So taking the inverse cosine of that gives us pi over 6. You may want to check all those computations carefully yourself. Let's finish up this section by looking at the equations of some familiar surfaces in all three coordinate systems. Let's start with a cone. Specifically, let's start with the cone z equals the square root of x squared plus y squared. Technically, this is just the upper half of the cone, since I'm only looking at the positive square root. Pause the video, try to write these equations in cylindrical and spherical, and then resume the video to check your answers. Remember that to convert between rectangular and cylindrical, we could use the formula r squared is x squared plus y squared. So we get the square root of x squared plus y squared is the square root of r squared, which is just r. So we have z equals r in cylindrical. Now to convert that equation from cylindrical to spherical, we could use our triangle here. Notice that r over z is equal to 1. And using either that picture or if you have the formulas memorized, we see that the tangent of phi is r over z, which in this case is 1. So that phi is equal to pi over 4. So this cone in spherical is the constant function phi equals pi over 4. Next, let's try a basic cylinder. Let's use the unit cylinder. In rectangular, that has equation x squared plus y squared equals 1. Once again, pause the video, try to write this equation in cylindrical and spherical as well. Then resume the video to check your answer with mine. For cylindrical, since x squared plus y squared equals r squared, we have r squared equals 1, or equivalently r equals 1. For spherical, we see that the sine of phi is equal to r over rho. And since r is 1, we have the sine of phi is 1 over rho. So we get rho sine phi is equal to 1, or equivalently rho equals cosecant phi. Let's try the unit sphere, which in rectangular has equation x squared plus y squared plus z squared equals 1. Go ahead, pause the video, and try to write this equation in cylindrical and spherical, then resume the video to check your answer. In cylindrical, x squared plus y squared is r squared, so we get r squared plus z squared equals 1. And in spherical, r squared plus z squared is rho squared, or equivalently x squared plus y squared plus z squared is rho squared, so we get rho squared equals 1, or equivalently rho equals 1. Finally, let's try a paraboloid. Specifically, let's look at the paraboloid that is written as z equals x squared plus y squared in rectangular. Go ahead, pause the video, write this equation in cylindrical and spherical, and then resume the video to check your answer with mine. Since x squared plus y squared is r squared, in cylindrical, the equation is z equals r squared. For spherical, we're going to replace z by rho cosine phi, and we're going to replace r by rho sine phi. Dividing out a rho, we see that we get cosine phi equals rho sine squared phi, or equivalently, rho equals cosine phi times cosecant squared phi.